And I'd like to welcome everybody to the WWV Amateur Radio Club August 2025 meeting. And today we're honored to have Vladi Gerginov, who is one of the inventors of the NIST-F4, one of the brand new additions to the NIST array of clocks. And he's here to tell us all about it. And I'm really glad that you're able to join us. And thank you again very much, Vladi, for being here.
Well, of course, you're welcome. I wish you guys could come and take a look at the clock. You're welcome to visit NIST. It's possible to arrange a visit. So if you want to see it in action, you're welcome. So
that would be great. Yeah, we would like to do that. We had a great visit, and it was wonderful having you guide us on back in 2023 when we had our club come down and visit down there. If you remember, we were down there. So
okay, great.
That was great. All right. Well, I'm going to turn it over to you. I'm going to mute everybody. So why don't you unmute yourself as soon as I mute everybody?
Okay.
And you go ahead.
All right. Let me try sharing my screen. Do you guys see the presentation?
Not yet.
Okay. How about now?
That looks better.
Yeah.
I'll try to make it full screen. How does this look like?
Very good.
All right. My name is Vladi Gerginov, and I am responsible for the operation and measurements performed with NIST-F4, which is the US primary frequency standard. We developed NIST-F4 in the last couple of years in collaboration with our colleagues here at NIST, Greg Hoth, Tom Hevner, Tom Parker, and Jeff Sherman, and also our external collaborator, Kurt Gibble. They all contributed to this work, so I would like to recognize their contribution. And with this, let's dig in. What is the reason why everybody is so excited about atomic clocks? What makes the atomic clocks so special, and why do we prefer atomic clocks as standards instead of very sophisticated mechanical objects? Well, a lot of efforts in the past have been made to make mechanical or crystal oscillators keep track of time, and it took only 2 years after the first demonstration of the first cesium beam clock in 1955. It took only 3 years to recognize its potential and define the unit of time, the second, through this special microwave transition in the atomic cesium. There were 2 reasons for that. First, people recognized the enormous potential of the atoms, which I will describe the reason for. And the second reason actually is not often mentioned. And what is important in the standard is not that it is extremely accurate, but it's only one of a kind, and you can't make a second one that agrees with the first one, which is the case with any mechanical object that we can manufacture. In contrast, the atoms of cesium or any other kind of atoms of the same type are essentially identical, which means that if we make 2 cesium beam clocks that are both 2 cesium clocks that are both using the atom of cesium to define a specific frequency, or as I said, to define the second, they should agree as far as we do our job well within the technical issues. they should always agree. We don't have to worry that the cesium to make the cesium atoms exactly the same. And this is what makes the atoms so powerful in terms of their use to define frequencies or to define the unit of time. You know very well stability versus accuracy issues. What we are interested in making a standard is not just that the standard is very stable and doesn't drift and doesn't show any poor stability, but we also need a standard to be accurate. When we make a standard, we are not allowed, especially a primary standard, we are not allowed to calibrate it with respect to any other frequency tool. A frequency standard, primary frequency standard, cannot be externally calibrated. It can be compared to other primary standards, but we should be able to define its accuracy from first principles, and we should not need external calibration to make it accurate. And this actually what makes making a primary standard very hard. And this is what took our team almost 4 years since we started working on NIST-F4 to turn a fountain that was actually having all the necessary signals and seemed to work okay. It was pretty stable to turn it into what we call a primary frequency standard, which means to have an accuracy which now reaches 16 digits. That means that if we measure the length of the second with this instrument, we could write it down with precision of 1 and then 1 point and then 16 zeros behind. What makes the atoms so interesting? Because of their properties, which are dictated by the laws of quantum mechanics, every atom has a structure. It has specific energy levels, and some of these energy levels lie in the optical domain. They lie in the microwave domain. The transitions between them can be very precisely defined in terms of frequency, or the resonances between these states, energy states, are very precise. And because the energy difference between two energy levels corresponds to a frequency, and it's only proportional, the only constant of proportionality is Planck's constant, which is a constant of nature, and as far as we know doesn't change. Measuring the energy difference allows us to measure frequency, and if one measures frequencies or oscillations, one essentially can keep track of time. How this is done, I'll give an example. A mechanical clock. So it has an oscillator, which is, in the case of a pendulum clock, it's the pendulum. It has a flywheel or some kind of object that the oscillator kind of moves. And then there is a counter. In the case of a mechanical clock, there is a mechanism that essentially clicks every second and gives you ticks that correspond to seconds. And not only that, the clock needs to keep the interval between two clicks equal to 1 second, but also it shouldn't lose track of the previous one. So it's a device that has to kind of continuously provide these ticks, and it should keep, maybe that would be understood better if I say it should be essentially keep track of phase, or the relation between these ticks has to be maintained. It's not only about the length of the second, which could be measured for a short time, but it is also keeping track and recognizing the individual seconds and labeling them. This is what timekeeping is. It's slightly different from just measuring frequency. Keeping track of time is a continuous process that requires continuity. How does an atomic clock work in that simplistic explanation picture? Well, the atomic clock essentially looks at the rate of the flywheel oscillator that is driven by an oscillator, it looks at the rate, and then it can measure this rate with respect to a transition in the atoms. If the frequency of the flywheel is the same as this very narrow frequency resonance in the atoms provide the feedback that tells the oscillator, okay, the frequency is correct. We see that, so your rate is correct, or if not, there is feedback mechanism that could slow down or speed up this oscillator. And what one should realize, and this is not always appreciated, is that in that respect, the atomic clock is actually not a clock. The atoms don't keep track of the seconds. The atoms keep track of the rate of an oscillator that you used to define the seconds, and they're essentially a tuning fork. They tell you if the rate of that oscillator is correct or not, but they don't know about time. They forget time, as I will explain on the next slide. Every cycle of these clocks, which are typically pulsed devices, every pulse of the atomic clock, the phase information is lost. The atoms start measuring the transition frequency from scratch. They don't remember what happened in the previous cycle, and from that point of view, they're not a clock. They're just a tuning fork or a frequency reference. But we call them atomic clock for basically I don't know, historical reasons. The first generation cesium clocks, probably some of you are, or all of you are familiar with these instruments. They're still manufactured and still celebrated and sold, are thermal beam clocks, where a cesium oven is used to generate a beam of atoms that propagates through a shielded environment into which one has a microwave resonator that looks like this U shape here. The idea of that resonator is to provide two zones where the atoms can interact with the microwaves. First, before entering the microwave zone, the atoms are state selected, or we just pick a specific transition, or atoms that are in a specific energy level, not transition, energy state or energy level. The rest of them are lost because we are not interested in them. That is a specific energy level that we call a clock state. And the atoms in this clock state are the only ones that are allowed to propagate through the microwave region. If the microwaves are on resonance, the atoms are excited and they change their energy state. They pick energy up from the microwaves, and then another state selection mechanism, which is a permanent magnet, non-homogeneous magnetic field, sends the atoms to a detector and we get a signal. If the frequency of the microwaves is not correct, the atoms don't exactly make it, or some of them only make it to the detector, and the signal is not as strong. And we get this characteristic shape called a Ramsey picture, or Ramsey fringes. You could see it here. The resonance is the one in the middle at 0. And then as the microwave frequency is detuned from resonance, you get these characteristic oscillations called Ramsey fringes. This is a quantum mechanical effect that is a result of the interference between the microwave phase and the atomic phase. And we get a resonance that is around 100 hertz wide. The central fringe is 100 hertz wide, and that's why this scale here is in kilohertz. People were, of course, never satisfied with anything, so these 100 hertz wide resonance seemed too broad. They tried to find ways to make the resonance narrower, and the width of this resonance is essentially determined by time of flight. It is a time of flight broadening. The atoms don't spend enough time between interacting with the microwaves because they're very fast. They move at the speed of a fast train through this relatively small instrument. And so the time they spend in the microwave field, interacting with the microwave field, is limited. So the first idea, the moment people started realizing how great these instruments are, the first idea they had is, how about we just flip the thing up and the atoms then go vertical, and they will slow down in gravity. Some of them are going to be so slow because it will take them a long time to cross the microwave cavity, and so the resonance is going to be very narrow. People tried that. They experimented with beams, they experimented with very, very long beams, and due to technical issues, they couldn't detect any slow atoms. So the hot atoms, or the fast ones, would keep pushing the slow ones ahead, and so they couldn't find really this narrow resonance due to the slow atoms that they were expecting, until in 97 a couple of brilliant people realized that they could use laser light to cool the atoms down and slow them down, and this made all the difference in this with this idea of using slow atoms to narrow the resonance, the atomic resonance due to the time of flight. And this is the implementation of the slow beam idea taken to an extreme. It's called an atomic fountain. This is what NIST-F4 is. The fountain uses a chamber where the atoms are laser cooled, which means they are slowed down. Their motion is slowed down to fractions of an inch per second velocities, and then a laser pulse coming from below and from above through this vertical structure pushes the atoms, or kind of gives the atoms momentum, and they fly up through this tube. If it were a beam, if there were no gravity, they would continue, and we could make our U-shaped cavity and pass twice through it and detect the atoms somewhere in the top. But because we have a gravity, the atoms go up, they reach some place in the middle of this shield where the magnetic field is very homogeneous, and they reverse their momentum and they fall back down a second time through the microwave field that excites them, completing what we call this double interaction, or the Ramsey interaction, and gives the corresponding Ramsey fringe picture, which now looks very different from the one you saw before. The scale here is in hertz, and the central Ramsey fringe is on the order of 1 hertz. So we have 100 times narrower resonance, and it makes 100 times better clock, because you now have to work 100 times less to have the same resolution of to figure out if the microwaves are on resonance. It shortens the averaging time, and additionally, it provides some interesting benefits compared to beam clocks. One is that the atoms go twice through the same microwave field instead of 2 zones. This eliminates imperfections in making this U-shaped microwave cavity that the beam clocks have, and that makes the instrument even more accurate than expected. And as I said, this 100 times narrow resonance allows these instruments nowadays to reach 16 digits of precision. A little bit details about NIST-F4, and especially the structure that we spent a lot of time developing, these microwave resonators that we have spent time developing. The only artifact, or probably the only part of the instrument where one needs to be extremely precise, is manufacturing these cavities very accurately. And the reason is that these cavities can actually influence the accuracy of the instrument if the phase of the microwave field inside them is not very well defined. And to make it as good as we can, and to be able to model it, we have to manufacture these resonators with extreme precision. So the cavity is first machined, and then it is polished, and then it's assembled. We measure the resonance, and the resonance has to be measured with an atomic clock, because we need to have the cavity exactly on resonance. And the instrument that scans this transition, or this resonance in the cavity, has to be accurate. So we reference that with an atomic clock. And then if there is an offset with what the frequency is, the center frequency here, as you can see, is offset by 5 megahertz. We go to the machine shop and we tell them to take some of the thickness of these end caps or these lids of the cavity, which is a cylinder with like a tuna can with two flat caps, to kind of take a little bit of material, typically with small steps of like 10 ppm or 5 ppm, until finally the cavity is tuned on resonance, and we could assemble the fountain clock. So this microwave cavity has a quality factor of 30,000, which is only 10% below the theoretical Q value. And part of it is due to the fact that the aluminum has a finite, the aluminum structure has these openings for the atoms to fly through that, through the openings. They fly vertically through the cavity. And in a minute, you're going to see a video about it. And then also there are holes here on the side that are used to excite this resonator. And the resonator is excited from 4 sides simultaneously for symmetry. Each of the excitation feeds for that cavity is coupled to an external resonator, which is a rectangular resonator out below that lid over here, which allows us to have a very, very symmetric distribution of the microwave field inside. The symmetric feeding is to avoid any running waves that come from one side of the cavity and get absorbed on the opposite side, since the copper is not perfectly conductive. And to make the cavity as symmetric as we can, the reason is the main reason why we have 4 independent feeds of the cavity. So let me show you an animation our Office of Public Affairs made of how NIST-F4 works. After that, I'll keep talking about it a little bit, and then when the presentation is over, of course, I'll stop for questions. But bear with me. Let's see if the video works.
So we're not getting audio.
All right, maybe I have to. Do you still hear me?
Yes, we can hear you.
Is it okay if I narrate this? I don't know how to turn the video's volume, the video sound on.
Please do narrate.
Okay, I'll try to do that. So keeping track of atomic time at NIST, or the US standard time at NIST, starts with the hydrogen maser. I will go back to the hydrogen maser as an instrument, and the cesium found the hydrogen maser is the flywheel oscillator, and the fountain is the tuning fork that calibrates its rate. The fountain consists, so the fountain is the tuning fork, and it consists of a lower chamber where a bunch of cesium atoms are cooled by using 6 laser beams, 2 vertical and 4 horizontal, to cool the atoms down. The cesium atom has 2 energy levels, or system of energy levels, and we are only interested in 2 of them that are a little bit broader dashed lines here, the orange one and the blue one. Initially, the lasers leave all the atoms in one of the manifolds of states, all in blue, and there is a special state selection microwave cavity that picks only the ones that we are interested in and puts them into one of the orange clock states. The atoms now are only in the orange clock state, and they go up in the fountain, reaching the Ramsey cavity, where they meet the main microwave signal. The microwave field can excite the atoms between the upper and the lower clock states, like a flipping coin, and they oscillate. This transition corresponds, or this oscillation corresponds to 9 gigahertz. They go up in the cavity, go back down, and interact the second time with the microwaves. It allows them to be compared properly with the microwaves, and then we detect how many atoms are in the upper clock state and in the lower clock state after the microwave interaction. If the microwaves are on resonance, we expect to see 50-50 number of atoms between the upper and the lower clock state. If the transition in the microwave frequency is not correct, then we don't get this 50-50 transition probability, which we aim for, but we get 30-70, let's say. We tune the microwaves until we get the 50-50 ratio. Once we have the microwave frequency on resonance, and remember that microwave frequency is related to the flywheel oscillator, which in our case is a hydrogen maser. We know we know how to calibrate the hydrogen maser to make it agree with the cesium frequency. So the cesium atoms derive signal from the hydrogen maser, tune these frequencies on resonance, and it turns the hydrogen maser into an accurate device that now realizes the unit of time, the second. How this is realized is by counting oscillation number of the microwave frequencies, and if you count the microwave frequency at 9 gigahertz, you basically have to count 9 billion cycles of that frequency to get 1 second. And then you count another billion cycles, you get the next second, and you keep track of the seconds. We need the hydrogen maser because it's an excellent flywheel oscillator. It is a passive device. It works all the time. There is no lasers involved. It can operate for years uninterrupted. So it makes an ideal flywheel oscillator, in contrast to the fountain that, as I said, only knows about frequency, and it's picky because it has lasers and other technical aspects which require it from time to time to be taken offline for calibration or for tuning, and cannot be used to keep track of time. So our time scale is essentially maintained by an ensemble of hydrogen masers and a fountain primary standard that checks their rate and keeps it locked to the length of the SI second.
Wow.
So NIST-F4, as I said, reaches 16 digits of precision, or in fractional frequency, 10 to the minus 16. And there is pretty much every single known physical mechanism can lead to disturbance or bias of that frequency. We need to know the magnitude of this bias or shift. We create an uncertainty table that measures that calibrates that shift. The correction is applied to the fountain frequency, and the corresponding uncertainty, or how well we know any of these different shifts, is how we end up with what we call a total uncertainty or a total accuracy of the fountain. So the accuracy of the fountain is on the order of 2 parts in 16. That's 16 digits of precision, and that is, if that is impressive for you, the next generation of optical clocks reach the next generation optical clocks reach 19 digits of precision. The reason for the 19 digits is because they are running, instead of microwaves, they're using optical fields for exciting the atoms, and the optical frequencies have orders of magnitude higher frequency, and allows you to essentially resolve individual oscillations to a much higher precision. But until the definition of the second is tied to the cesium atom, the primary standard for the SI second, or the unit of time, remains cesium, and the atomic cesium fountains are still the primary frequency standards. Once a primary standard is accepted by the international community, it can be used to steer the International Atomic Time, or TAI. That is the basis of UTC. UTC is essentially TAI plus extra leap seconds. And this table demonstrates historically the primary and secondary frequency standards contributing to for the calibration of TAI. The region in orange are all fountain primary frequency standards that were ever built. The green points mean they have been used live to steer TAI. The gray points show periods where the fountain reported data, but it was taken a long time ago and cannot be used to actively steer TAI. And the top section of the table or the plot shows the contribution of the secondary optical frequency standards. They start to become online, but they're still not as often contributing as the microwave ones. And you could also see that the former NIST primary frequency standards, NIST-F1 and NIST-F2, stopped contributing on the around 2016, and since then NIST doesn't have any contribution. This table is probably going to change in a month when the first contributions from NIST-F4 are going to be recognized. So we'll start getting a new line is going to show up in this table, and we are going to start getting contributions from NIST-F4. But it is a very slow process because BIPM is very conservative. So we have to wait for their approval. Actually, the approval arrived, but for them to implement the contribution of F4 to TAI. This is how TAI looks like with two fountains only shown. The black line is what TAI does, and the orange and the green points are contributions from a German and a French fountain over the last couple of years. You could see that the accuracy of TAI is now, the stability of TAI is now reaching fractions of 10 to the minus 15, or several parts in around between 1 and 2 parts in 10 to the minus 16. And each of these data points represents a campaign that is at least 10, maybe 15 or even longer days of continuous fountain operation. So it takes a lot of work to run a fountain clock that involves lasers over days and weeks at a time and contribute regularly as these two instruments have managed. We are trying to do the same with NIST-F4. So far, we have around 11 contributions, and we hope to keep up the uptime and to start contributing regularly and show an improvement of TAI. And with this, I will finish and leave some room for questions. These are pictures of our two fountain clocks. F4 is here on the right. F3 is not the primary standard. We don't try to make it very accurate. We just rely on its internal frequency stability. It doesn't have any drift. So we use it, again, to calibrate changes in the rate of lasers. But F4 is the one that carries the weight of accuracy of our time realization. And yeah, with this, I would like to thank the people who helped for this work. And please let me know if you have questions.
Well, Vladi, thank you very much. It was a really good overview of the whole thing. It's really interesting to look at it and to think, the original clock was horizontal, and then it ends up just making it vertical. That was I guess I never thought of it that way, but that's a great way to think of it, and to develop the new clock. I had a couple of questions. When you showed that last image just a few slides ago, when you were comparing over maybe a 10-year period, and they were comparing the French and the German clocks, why were they that particular slide? The variation, say, from 2019 to 2020, they seem to have matched each other. Why would they be matched up like that?
Sorry, I don't understand what you mean by they've matched each other.
Well, the yellow and the green are both, they both moved down 2019 to 2020. They, were very close to being the same offset. Is that correct?
Well, yeah. So basically, it depends on how BIPM decides to steer. So TAI's backbone are clocks that are having drifts, and this is an ensemble of hydrogen masers and so the rate of this ensemble is calibrated by the fountain clocks or the primary standards, which don't drift. And the IPM's algorithm in the beginning was very conservative. So even if the fountains would tell BIPM, hey, the rate of TAI is too high or too low, they would not steer very fast. They wanted kind of long-term stability, so they wouldn't go and very quickly start adjusting the rate of basically an ensemble of free-running drifting clocks. And after they kind of got confidence and the fountains started contributing more regularly, because if you see on that slide here in the beginning, there were fewer contributions, fewer fountains, and also their errors were bigger because things slowly got better and better in historically. So when the fountains became more available and more accurate, TAI became more aggressive in steering. So they essentially improved their algorithms and could correct the free running ensemble of clocks faster with the fountains, which made the TAI agree better with the fountain clocks.
Is that why when you get to 2023 and 2024, it's much more stable or
Yes.
closer to zero?
Yeah.
Very, very good. Okay, that makes much more sense.
Yeah, and the small variations here is because there are, as I said, maybe 10 to 15 fountain clocks that contribute from time to time. There is some optical clocks that do, and some of them sometimes have statistical issues or noise issues. And so this is an average, running average over all of them in some complicated algorithm. And so it's not always possible that the black line goes through all the data points. Some of the fountains agree better, some agree worse, but the whole goal is to keep the black line as close to the average of the fountains as possible.
Very good. And my other question was, when they do the machining and they're taking off 5 to 10 parts per million of the width, what's the time that it takes to assemble the clock, see that it's off, disassemble it, remachine it, and then test it the next time? Is that weeks or is that matter of days?
Well, so it was my job to do that, and what I did was I didn't have to put it in vacuum. So I would assemble the cavity and I would measure its resonance in air, and then I would correct the frequency with the shift that the air would cause, which is around 2 megahertz. So I basically had to have the cavity too small by a certain amount. So it was around 2 megahertz detuned from resonance before I put it in vacuum. And the idea was that if that was not correct and I measure in vacuum the wrong frequency, I would take the fountain apart, get it out, and then repolish and change the dimensions. But we were lucky to have a good estimate of what the air does, and so we didn't have to do that. So the measurements were done in air, but yes, the cavity had to be fully assembled with all the screws in place. We had to let it thermalize because you don't want to get it off the lathe like hot after being machined or something like this. So we took a lot of care. I think the whole process of manufacturing the cavity took, I was in the machine shop around 3 months working with the machinists to kind of make sure that we don't make a mistake, because that could be costly. As I said, it took 4 years to evaluate, to kind of make F4 work. So you don't want to make a mistake and have to go back and repolish and realign the cavity especially after putting it in contact with cesium. If you oxidize copper that has been exposed to cesium, it becomes a mess. So you have to start from scratch pretty much.
A question or comment. I suppose that's the kind of situation where you don't want to ever take off too much.
Yes, in general, we made the cavity too small on purpose, and then we would polish the lids only, and we don't touch the walls. There is a way to make it too big by machining a different part of the cavity, not the polished part, but another one. We didn't have to do that because I would not allow them to, if I had to make an adjustment of the height, I would tell them to make half of the value that I really wanted, so that there was room for mistakes. And we often, I mean, there were mistakes. Sometimes I would tell them 5 mils, and they would take 10. So we had to do that very carefully, but luckily we didn't have to. It's not the end of the world. It can be made bigger if one has to do that, but we never did manage to make it too big.
You had a photo right at the end of the fountain, but I have no sense of scale for this. Can you describe it, the physical size of the apparatus?
So this is pretty much 6 feet. From that level here where some of the optics is to the top of the fountain is 6 feet. It's really tall. F3 is a bit smaller, so I would say this is like human size from the top to here. But actually, this is probably more than 6 feet. I would say maybe 7 feet is F4, and NIST-F3 up to here is maybe 5.5. It's a big instrument. It has to be leveled very precisely, so it's on a big optical table with adjustable, so it has to be leveled so that the atoms fly exactly vertically. But yeah, it's a very big instrument. It takes a whole lab, and that's only the physics package where the atoms are. There is a whole other table where the two lasers that cool the atoms and probe their energy levels are. So it's two big optical tables in one big lab.
When you have a device this large and yet you're still relying on the precision cavity that's inside of it, the temperature stability of this must be critical. Or do you just compensate for temperature variations?
You're absolutely correct. So so the cavity is very massive. It's made out of copper, and it's inside vacuum. And the outer wall of the cavity, which is this gray zone here surrounding the cavities, is aluminum tube, on top of which we have wrapped a non-magnetic heater, so that we could change the temperature of the whole structure and thus change the temperature of the cavity. And because it's so well isolated and so massive, the time constant of the cavity is around 1 day, and then the center frequency has to be kept to within the temperature has to be kept to within a fraction of a degree, so that we are on resonance. And we have in the lab around 0.2 Kelvin temperature stability, and it has to be absolute temperature stability. So there is a servo that we could engage to keep the cavity on resonance if the lab temperature changes. Luckily, the lab has a very stable air conditioning system, and we spend a lot of time maintaining that temperature. But yes, you're absolutely right. This is a high Q cavity that is very temperature sensitive, and half a degree change in room temperature would stop the fountain from working properly. So we discard data if the cavity is not on resonance for any reason. The nice thing about the long time constant, though, is that it kind of rides out things like opening doors and daylight versus night, daytime versus nighttime temperature swings, if there is any residual temperature swing. So yes, it's actually the only mechanism, like the most often case of the fountain malfunction is failure of the environmental control in the lab. The lasers are also very temperamental, so the lasers are not anymore on resonance, and then the cavity is not on resonance, and I have to wait for a day until things get back to where they were.
I have a question concerning why cesium as the atom of choice, and is the F3, F4 transition have something special or unique about it that makes it more advantageous to use?
Well, it's very easy to measure the clock frequency at 9 gigahertz using electronics. And also the frequency of cesium is the highest because it's the heaviest of the alkalis, apart from francium, but of course it's radioactive, so you don't want francium. So you want the frequency to be as high as possible because that improves your clock performance. You want it to be in the microwave domain because back in the 70s, that was the only frequency one could measure. Only nowadays you could measure optical frequencies. So people picked cesium, and also cesium melts at room temperature, and you don't need to heat it up much to actually have a vapor. If you have the cesium in vacuum, it evaporates already at room temperature, so I actually don't need to heat the cesium source at all for the fountain to get enough density, vapor density. So it's easy to use. It has a convenient microwave transition, and it's the highest of the frequencies from the alkalis. Rubidium would have been probably just as good, but people just picked cesium and got stuck with it. I think it was a good choice. It still performs extraordinarily well for in the last 70 years. So I think it was the right choice back then.
One last question. How do you cool something with a laser? That seems counterintuitive.
Thank you, John.
Oh, that's a very, very good question. So imagine the cesium is like a projectile that flies against you, and you have a whole bunch of pebbles, and you start throwing it at the projectile. Every pebble would impinge some momentum on the projectile and then bounce off in random directions. And you could think about, if you throw enough pebbles, you could stop the projectile. The same thing the lasers are doing. They're sending photons against the direction into which the atoms are moving, and the atoms absorb these photons and then emit them in a random direction, but they only accept momentum from the direction of the laser. So the absorption is directional, and the re-emission of photons is uniform. So on average, each photon gives the atom a momentum that slows it down. And it's not as simple as that, otherwise there wouldn't be a Nobel Prize for laser cooling. But it turns out you could make a configuration of 6 laser beams and trick the atoms into always kind of interact with photons that are flying against the direction of the laser of the atom movement. And so essentially they get slowed down from all sides. In the fountain, the mechanism is called optical molasses. So it's like you put the atoms into something viscous and they kind of try to move, but the faster they move, the more friction they experience. And the friction is provided by the momentum of the laser light photons that hit them. So it's as I said, it's a neat trick, and I wish I came up with it, but it wasn't me.
Thank you.
Sure.
What's the influence of the gravity, intensity of gravity on the frequency?
So because the clock is in Boulder, there is the gravitational shift, or that is the essentially relativistic effect due to the time dilation in strong fields, strong gravitational fields. So our clock ticks faster than the one in at sea level, and people decided to define the frequency of the clock at sea level, or so-called geoid, and so we have to correct the fountain frequency because it's too fast. So when we compare with Europe, where the fountains are almost at sea level, our instruments agree. And the correction is in the table right here. It's the first shift is the relativistic shift right here is so 100 and almost, it's 10 to the minus 15, 14, 13, 2 parts in 13 shift.
So does this in principle you could measure gravitational waves by observing the changes in frequency?
Yeah. Yes. So the fountain can resolve altitude difference above the geoid of about one meter.
Wow.
And so the optical clocks, when they come out, would they be, they're 10 to the 19, so would they be down to 1 millimeter?
Yeah, so I think I got the number wrong. I think it's like 10 to the minus 7, 10 to the minus 17 per meter. So it's 10 to the minus 16 in 10 meters. So 2 fountains have to be off by 10 meters in terms of altitude to kind of have a measurable change of their rate. But with 3 orders of magnitude better performance of optical clocks, you could get on the millimeter scale, and this gets people very excited to do what they call relativistic geodesy, where they take 2 clocks, you compare their ticking rates, and you tell which one is higher than the other 2 millimeters, which is great. It's a dream that is coming close to reality nowadays. People make transportable optical clocks already, and they start to show, it has been demonstrated in the lab that they could resolve altitude, and people start to do geodesy using them. It's early days though, but it's very promising.
Very good. I'm curious, what point in your life did you decide you wanted to become a scientist? Was it when you were a kid in high school or younger?
I think probably when I read Jules Verne.
Okay.
Yeah, probably maybe I was like 10-ish.
Very good.
Yeah.
And what got you in the? How did you steer yourself through, to get to where you are now? Was that a?
Science
came naturally, and you just soaked
yeah,
it up.
yeah. I mean, I was interested in lasers, and so when I applied for a grad school here in the US, my advisor was doing cesium spectroscopy using diode lasers, and I thought, oh, cool, I could use diode lasers. And since I did my PhD on cesium, PTB got that's the equivalent of NIST in Germany. They got excited and said, hey, we would like you to come and work on the fountain clocks. So I spent 8 years there, and then moved back to the US recently. And I think it's because of my work on cesium, but I wasn't interested in cesium specifically. I just wanted to do laser spectroscopy. And it happened that my advisor, Carol Tanner, she worked with cesium her entire career, and I continued doing that. So I work on cesium since 1997.
Oh, very neat.
Vladi, I imagine you and the rest of the team that worked on the F4 will feel a great deal of pride the first time you see the TAI corrected by your F4 clock. Is that true?
Absolutely. Absolutely. It was like a birthday for me when the evaluation manuscript got accepted, and now the second birthday was recently. Actually, on the 22nd of August is when BIPM said, okay, all clear, you did your homework, we accept your results.
Congratulations.
Wow.
Thank you.
That's really exciting.
It's a big thing. I mean, it's 5 years of really hard work. And as I said, the club is very exclusive. There are only 20 of these instruments ever built. Only 15-ish of them still work. So yeah, it's an exclusive club, and it's hard to get into, and it gets harder and harder because things get better and better. So yeah.
Well, that's exciting. Really
Yes,
neat.
it's a big deal.
Yeah, it is. Other questions from anybody?
I'm
Well,
not sure. One question, and I'm trying to figure out how to phrase it or articulate it. I understand the sensitivity of these of the clocks to altitude, and you
Yeah.
mentioned that you can take two of them and relatively compare the altitudes. Is there a defined center of gravitational mass of the Earth above which that altitude is defined? Or how, how do you know what altitude you are above what?
Well, there is a whole team of scientists at NOAA where they do geodesy and leveling, and they have models. So it's a combination of instruments like satellite observations and gravitational, basically measuring small g, the force of gravity at different locations, and mapping this whole mapping the whole continental US, and basically creating what they call it's an artificial surface that is supposed to be the same gravitational potential. It's like a map, and there is a geodesy line that has the same gravitational potential. I don't know the details of that, so I tell them I need to know what the gravitational potential of the clock is. They come to the lab, they came to the lab, they installed the marker, they do their leveling, and they connected that marker to that model that they use, which has been updated recently. So NOAA has a website on this, and they claim the accuracy of that model with respect to the international grid geoid is on the order of 1 to 2 centimeters, so a fraction of an inch. How they do that, it's a different question. So it's not something that I'm an expert in, but it's certainly is possible. There are many methods, and they compare them all. One of the GPS provides to some extent possibility to find altitude with high accuracy, but it's not as accurate as other methods. And one of the things is really measuring local the small g, or local gravitational constant locally, and infer from that where this potential is, because it could depend on the density of rocks under the specific position. So it's not just geometric altitude, but effective height. So it's a whole new other business and research to calibrate the altitude.
Since the core is moving, I assume then that there's a recalibration that has to be done to your clock to compensate for that on a regular basis.
Yes, and they do that every couple of years. Luckily for us, one part in 16, as I said, corresponds to 10 meters, and that's quite a change. And they are not the drifts are not significant at that level. But yes, and with optical clocks, this will become even bigger issue, because once you have something that is sensitive to centimeters, and you start sending data to sea level, the disagreements are going to be then the question: is it that the clock is wrong because you didn't do your homework, or is it because something changed under border and changed the gravitational potential, and your clock reflects that correctly? So it will be a messy thing. So it's a whole new set of problems that are going to be faced by the optical clock people, who are very eager to have their clocks define the second. And these comparisons and these agreements that we now reach at low parts in 16, they have to prove that they could do better than that. It's not going to be easy. But you're totally right. There are tidal waves and things like this that for sure affect what is going on locally and how fast the clock works. And the calibrations, I mean, I wish they do that more often and have some kind of understanding of what is going on. But so far they have been doing that every couple of years only, and they seem to show consistent results. But it's a hard work.
It's interesting because the lab in Boulder is right next to the mountains there too, and I think that the gravity of the mountains would affect what goes on in the lab.
Yeah, and they come with instruments that measure the local gravity, and then they do some kind of ranging and satellite measurements, and they do GPS calibrations of antennas and leveling, and how they get to all these things to agree to such accuracy. Honestly, I'm amazed. But they come and they tell me they're amazed at what I do. So I don't know. It's just probably well understood. I just don't know it, and that's why it sounds beyond me. But I agree, it's beyond me.
That's the advantage of collaboration: getting together and put your heads together, and you end up with something greater than yourself.
And if they are wrong, I would know, because then I'll send my data and I will be off on that chart that I showed you, and that chart could be a badge of honor if you're right, but it's also like a grade for your homework. So you could get an F. So every month you kind of put your reputation on the line. You say, I think this is what TAI rate is, and they tell you, nope, you're wrong. So I'm confident that so far we have done our homework because they looked at the results and they didn't flag them as questionable. So it sounds good, but the gravity is one of the problems for Boulder. We are the only ones with such gigantic gravitational shift. PTB's fountain clock is 60 meters above the geoid, so the correction is even if they're wrong, they can't be wrong by much. They could just see where the the geoid is. It's very close to them. So,
are the issues in the was it the Colorado River by the Hoover Dam with the caldera moving with the lava flow underneath? Are you seeing any effects from that?
I don't know, and honestly, I don't know how I would see them because the only way to see them is if I compare with somebody else in Europe. And if we agree, which is the goal, then everything is good. If we don't agree, typically is that I did something wrong. I haven't. Nobody so far has used the excuse that something happened in the core of the Earth and that's why their clock is wrong. Typically, it's me not paying attention to a ground loop, which is like the bane of these instruments, or like an optical shutter that lets the lasers kind of change the clock frequency by exposing the atoms to light. The atoms are like the most sensitive probe. If you don't turn off your lasers, you could be off by as much as you want. There is no limit of how wrong you can be. But there is a limit. But you need to be as good as possible, and then you have to agree with everybody else. That is the hardest part. You could always measure something with the fountain, but to measure something to 16 digits and compare it with somebody else with completely different instrument and agree, it's actually, I still find it amazing that these things agree so well.
It is.
Over and over. It's amazing.
So the F4, is it currently operating?
Yeah.
Okay, and how long do you keep it operating? I mean,
so so sometimes you have to align the optics, because these are lasers and they propagate between mirrors. They go into fibers. The lasers are big, complicated instruments that need cleaning and maintaining. So I would say typically I have campaigns that last between 2 and 3 weeks, sometimes 30 days continuously with 99% uptime. and
Wow.
then I would go and start maintaining, essentially bringing the parameters back to where I would like them to be. And if there is technical issues, you don't report. But in principle, the fountain is 24/7 working. It's doing something. If it is measuring time, is a different question. But operationally, it is always on. I don't turn off the lasers unless there is a power outage that lasts days and there is no need for them, or the air conditioning is out for days and they don't need to kind of operate and get to age. But typically that happens over a day, and then the next day things are back to normal and I keep measuring. Not always calibrating the masers, but I would say 70% of the time the fountain is contributing to the time scale calibration of the time scale ensemble of masers 70% of the time. And the more I know about it, the less I have to check things. So one reason why it took years to evaluate it is I get 16 digits, but I get 16 digits after 2 weeks of measurements. So imagine you have to check for something. You change a parameter and then you wait 2 weeks, and the answer is nope, that's not it. That's not the problem. You change another parameter, takes you another 2 weeks. During these 2 weeks, your reference, which is the other fountain, F3, breaks down for some technical issue and the measurement is gone, so you have to repeat it. So for every single thing that you want to check, the averaging time can last weeks. And the only way to speed up the process is to say, well, maybe if I'm looking for a specific effect, like what are the lasers doing to the fountain frequency, you amplify the effect somehow. So you make more light, or you keep some shutter open to let more light in, and then you measure the shift is bigger, so you don't have to average to the 16th digit. You can average to the 15th, which saves you a lot of time. But this is the biggest, I would say, that is dooming the fountains as in the future, that it takes so long to get to the 16 digits. The optical clocks have the unfair advantage that they could measure 16 digits in a couple of seconds. So it's not really a fair game. You could do a lot more with your time than if you have an optical clock than with the fountain. So they could make a comparison of the 16th digit in a minute, and I have to wait 2 weeks. It's like not fair. That's how I feel. They don't feel like this. They say, why does it take you so long? And I think it's not fair.
Well, you're going to stick with cesium, though, so that sounds good.
Well, I mean, it's not anytime soon that the second is going to be redefined. It is at least a decade away because people are very conservative. They don't want to make a change before they're ready. So cesium is going to be the primary standard for another 10 years. And so I'm not worried about being out of job. Yeah.
All right. Any other questions from the gallery? Well, Vladi, thank you so much for your time and
you're welcome.
Come with us this afternoon, and I'm glad that we were able to get you to come in. And it was a great talk, and it's really neat to hear from the guy that built it.
Yes.
So,
I apologize for the video, but if you guys want, if you go on the YouTube, you could see the video with the sound. I apologize that for some reason I cannot make it work from my presentation, but it's online, so you could check it out on YouTube.
right. Yeah, there's good places to go for it. Yeah.
Yeah.
And I'll put those links up on our website too.
Yeah, and the narrative is way better than mine because they spent like 6 months polishing the narrative. So it should be better than mine. And I wasn't prepared. I wasn't prepared to listen to the original narrative while simultaneously talking to you guys.
Yeah,
so, yeah.
That's hard to do.
You did a very good job. I thought it was
Thank
excellent.
You.
So yeah, and the videos, you know, your writing team at NIST is very good, and they put together a really excellent program. So it is. Everybody go to the NIST site and look this up. It's great.
Yes,
really
and please come and visit the fountain. And you could arrange a tour. It's not a problem at all. You could see it, and as I said, it's normally working. So you will see the signals, you will see the flashing of the lasers cooling the atoms. It's very exciting. Both of F3 and F4 are working, and you could visit them at any time. It's publicly accessible.
Cool.
Well, thank you for that invite. We will look into that. We'll look at our calendars.
Yeah.
So
Sounds good.
very good. All right. Well,
Thank you
for
very much.
being here.
Oh, you're welcome.
And, you're welcome to exit. We're going to do
Thank
a little
you.
club business.
Wonderful.
As well,
Okay.
but very little. So
Sounds good. Thank you for
Right,
your
thank you.
attention, guys.
yeah.
Bye.
Thank you.
Presentation.
Thank you.